I forgot to hit record again during the part where we went over the answers to the worksheet, where the students gave me their answer, and either it was already right, or I kind of helped them kind of see where their thinking lied, and where the more accurate answer, perhaps, where they were kind of not quite seeing in some of these problems. Now, let's start with the first one, which is NBS, or N-bromosuccinimide. And that has a chemical structure, although you don't have to know it because you can just memorize what its function is. But it has a chemical structure of a nitrogen in a 5-carbon ring, where the neighboring carbons to the nitrogen are these carbonyl, that is C double bond O groups, and you got this bromine kind of dangling off like this. And I think we'll see structures similar to this. Just the main idea, these carbonyls, or C double bond O's, they help stabilize anything that forms in this nitrogen, whether it be an anion lone pair or a radical, and thus making the generation of a bromine radical more susceptible upon meeting some kind of either light or other radical initiator, perhaps even under heating conditions for the case of benzylic bromination. And so essentially this leads to the formation of bromine radicals without using Br2 directly. Reason to avoid that, as we'll see, under the right conditions, bromine can react with the benzene ring, as in chapter 18 we'll talk about that. You can control that by not having the necessary catalyst in here, and also working with bromine itself. Br2 is dangerous. I think those reasons, and maybe even some others, NBS, or N-bromosuccinimide is a common go-to for bromination, even actually sometimes an allylic, that is to say, when you have an alkene. We saw this last semester as well. And so mainly the idea here was, where do we put that bromine? Bromination, free radical bromination, if you don't remember, is due to the removal of a hydrogen via a radical process, leaving a radical behind on the carbon, and then having that radical react with bromine to end up with a bromine at that site. So really the key idea is, where are there hydrogens that you could remove? And so I'm not going to draw every single hydrogen. I'll just draw all the unique ones. So these are several of the hydrogens that you could have. I mean, there's also the ones on the benzene, but as we'll recall, cations don't like to form in sp2 carbons, nor do radicals. They're not favorable. And so definitely you avoid sp2 carbons, but then you've got these sp3 carbons that all have hydrogens on them. One that doesn't is this one right here. There's no hydrogen on this, and so that is not even an option. And as we'll see, that might be a trick, or that might trip you up, because you hopefully recall from the video and in our discussion today in class that it is the benzylic carbon at which most of this chemistry takes place, because the benzene ring stabilizes the intermediates, or even transition states, if it's a one-step process, for most of this benzylic chemistry. And so that's what happens in free radical bromination. We're going to actually have the hydrogen that is located on the benzylic carbon, in the benzylic position, be the one that turns into a free radical intermediate, and then eventually run into a bromine, whether it be a termination step, as we learned in chapter 10, or a continuation of propagation, or it runs into perhaps a bromine Br2 molecule. You might say, I thought you said there weren't any Br2 because it's dangerous. It turns out N-bromosuccinimide not only generates bromine radicals, they eventually form Br2 even. It decomposes into Br2. Not only during the reaction, even on the shelf. So Br2 does form in this compound. It exists in there, or eventually forms as you heat it and let it react. So whatever route, the radical intermediate that we form at this carbon because of the stabilization due to the benzene ring, eventually that radical runs into a bromine atom, and the bromine ends up there. I don't want to go over the detailed mechanism of it because that was Chapter 10 in OChem 1, but essentially it's the same mechanisms we learned for radical mechanisms of bromination of alkanes or alkyl carbons, but it's quite favorable. In fact, it's the most favorable at a benzylic site. More so than next to just a regular old double bond, and definitely more so than a sp3, or excuse me, I should say in a regular carbon that is not near any benzene or alkene double bond allylic site. So this is the most stable intermediates, thus the bromine ends up there. It would end up here if there was a proton to be abstracted, but because it's quaternary or it has 4 carbons connected to it, no hydrogens, no free radical bromination can occur there. These other ones don't happen because they're just not stable enough. They could hypothetically happen, but their intermediate is so much higher in energy and not as stable as the radical intermediate that would form at this carbon that they just don't even get explored in the course of this reaction. Even as they randomly collide and try things, this is just energetically way more favorable. So this is the main product. Well, right over here again. It would be the benzene ring drawn all over. Really nothing changes when you've got these chemicals except the addition, or it's not really an addition, but the substitution of a hydrogen. What was once a hydrogen at this site. Let me erase it back to normal, back to what it looks like on the worksheet. The bromine's not really there yet because it's on the reactant side. And now there's a bromine where once there was 2 hydrogens here, now there's 1 hydrogen that we don't draw according to bond line formulism and a bromine. And then we also have, where's the rest of the compound? This right here. Another trick that would happen, or another thing you might get tripped up with, is you may remember from Chapter 10 that the tertiary carbons are more stable radical intermediates, and that's true, but just regular, not next to any double bond or benzene rings, tertiary carbons, they're not as stable as even, this is secondary, but it's next to a benzene ring. That's the most stable, or at least leads to the most stable radical intermediate, free radical intermediate. So it goes here and leads to the bromine ending up there. So in this example, what we have, first of all, we have NaOCH3, and this is excess. It took me a while, even after when I first got this textbook and started teaching from it, to realize what they meant by this. It's literally just saying the letters XS, excess. In other words, it's excess of this reagent. In other words, more than 1 mole, or molar equivalent, than the moles of this. So it's more, it's 2 or more, and it's excessive amounts. So in other words, there's plenty of NaOCH3 in solution to react more than once with this molecule. And that is what it's going to do. And so what is NaOCH3? Essentially, it's OCH3 with a negative charge on the oxygen because it has lost a hydrogen more than likely. It used to be methanol. And so this methoxide, it's a strong base and it's a strong nucleophile. However, these carbons, well, they're benzylic first and foremost, so that makes them highly reactive. However, the substitution will not be favored because they are secondary. And so under these strong base conditions, more likely, and it is what happens, we're going to deprotonate the beta hydrogen. And so we have 2 of these, remember, in solution. And so each of these is going to deprotonate. Now where's it going to go? Remember, it's towards the leaving group, the bromine leaving group. It's going to fall off, and so these electrons are going to let go. These electrons, and by the way, I'm drawing these all in one thing. I mark people down for this all the time for mechanisms. I'm not doing a full-on step-by-step mechanism. I'm just kind of giving you can do this on your exam or problems if I'm not asking you for a step-by-step mechanism, but you're trying to either leave me some information of what you were thinking for partial credit-wise, or just on your own, you're just trying to solve the problem. You could do this, which is just kind of quickly thinking through, what's all this stuff going to do? Essentially, 2 eliminations is going to occur because there's 2 good leaving groups. Granted, this was a more challenging problem. So if you were in class and you happen to be watching this for some reason, again, maybe reviewing for exam 2 or something, that may have tripped you up a little bit, but it's not too hard to, when you have excess reagent and you see 2 functional groups or 2 common structures that lead to reactivity, to consider multiple things happening. or things happening twice, with the exception of if we learn something very specific, some specific set of, two functional group structures that does something else than, some other reaction we've heard of happening twice, some new reaction we learn about maybe happening. And I can think of one thing like that in Module 3 we might come across. But instead, it's just 2 elimination events occur. The other thing I mentioned in class, when the student had given their answer, which, if I remember, I think was close. They hadn't finished it. They didn't do a second elimination. But the reason why you would get a second elimination, definitely, and not a substitution or have it just sit there, is because by doing the double elimination, what you've done is you've generated not only conjugation, but it turns out, if you think about it, this looks like is a benzene ring, and so it's aromatic. And you could think of this ring as aromatic. This is known as a polycyclic aromatic, a PAC. And so when you have these fused rings where both rings are aromatic, that's also got special stability characteristics. So this is a quite stable product to form, and it does. The last one is oxidation, where you've got this sodium dichromate, sulfuric acid, and water mixed into this starting material here. And the key is identifying where the benzylic carbons are. And so these 3 carbons are the benzylic carbons. Now, it's not only that, as we learned about in the video, because the mechanism for this we don't go into, because many people theorize that it involves some radical intermediates, and it's more complex than what we're going to go over in a sophomore organic class. But one of the requirements that is observed is that in order for oxidation to take place at the benzylic carbon site, which it will, if there is a proton attached to the benzylic carbon. So like in this example right here, there's 2 protons at it, and there's 2 protons here. But on this one, there's no protons. So if there's no alpha protons, there's no benzylic hydrogens, then it's not going to undergo oxidation. So the product in the end ends up being the benzene ring remains untouched. It doesn't do that. These reagents are all happening at the benzylic site. This one remains unreacted, this chain right here, because there's no benzylic hydrogen to get it going. But these have it, so they undergo the reaction, in which case everything is stripped off of them except for 1 carbon that's double bonded to an oxygen and single bonded to an OH group, like this. Here's one more. So in this molecule, this was a challenge problem. And so you have 1 mole of sodium thiol. I think it's thiol, but you've got sodium SH and Na+, and then you've got this right here. Essentially, it behaves like hydroxide or an sodium hydroxide. So you got an S with a negative charge on it. This is not very strong of a base, however, it is a strong nucleophile. And so you got these 2 primary carbons that are susceptible, being primary, to an SN2 reaction, a substitution event. Now, the whole challenge here is you only have 1 molar equivalent, and what that means is, more than likely, only one of these sites is going to react, because whichever site does react is the one that's going to be the more stable electrophilic site, something that's stabilized in its positive charge, because it helps it react as the bromine falls off and draws the nucleophile to it. And so it is ultimately going to be the benzylic carbon. That was kind of the key to it. This is not a benzylic carbon. It is a primary, but this is the benzylic carbon, and so it is going to attack it with an SN2 reaction, not the primary non-benzylic carbon site. And so in the end, if you only have 1 molar equivalent, you will end up with the following final compound, where you've got the benzene ring, you've still got the 1 bromine on here, and instead of a bromine on this site, you have the SH, the nucleophile that was attacked.